So hello everyone. I am Debabrota Basu. I am a researcher in India Lil, and today we'll talk about how to go from discrete to continuous in RL. What are the techniques out there, and what are the things we know? So with France, you have seen a glimpse of like how the discrete MDPs work, discrete POMDPs work. Now the question is how we go to more continuous. So as you see, like the title of the talk has changed a bit from what it was written. And now I like to call it the actors and the critics. So basically we'll talk about how to use function approximation and policy gradient methods for reinforcement learning. So without further ado, let's start. So I hope like by the end of the lunch, you didn't forget most of the thing. So still we'll try to recap a bit. So this is one of the environment that we have developed. So maybe people have heard of GYM, the RL gym environments where you can go and test different algorithms, right? So this is called a farm gym where actually you can play the role of a farmer and you can really have different plants. You can put them, you can harvest them, you can put pesticides and stuff. And your goal is actually to look into this environment and try to optimize the total amount of harvest you are going to do in the end of a season. Okay. So this is a typical RL environment where the goal of the agent is to maximize a certain utility, in this case, the total amount of the harvest. And the person has access to lots of actions, like whether to put pesticide, whether to water the plant, whether to put herbicide, whether to sow the seeds up to a certain amount or not. So this, as we have formulate it as a Markov decision process typically. So I'll not go to POMDPs, we'll stay in the realm of MDPs completely. And as you see, like, or already have seen, and I tried to put a few alternative things since, we are talking in the juncture of control and reinforcement learning. So this is known in different communities in different way, like action, intervention, or control. We have states. Luckily, states are mostly state everywhere. And then the transition function, which we'll take as a distribution over the next states, given the present state and action. And the reward, which again we'll take as a distribution over the real scalar values, measuring the goodness of an action into a state, right? And the goal, again, you have heard all of this. Just to recap, because we'll need these expressions in a few moments, is that how we decide a policy, a strategy to take actions, are good or bad, by calculating its long-term return, right? And typically, again, as we have had different setups, we'll stay with only discounted reward here. Okay, people have looked into finite horizon cases, people have looked into like average reward cases, but we'll go for discounted reward one. So basically what we are saying that the goodness of a policy is the total sum of return, but discounted by a factor gamma to the power t. Okay, and why gamma to the power t? The interpretation is typically like if you take a decision now, its effect dies down over future, right? So what is more important now is less important later. And so the final goal is, if we agree this is the value function that we want to optimize with a policy given, that decides on the action given a state, then the goal is to find an optimal policy that maximizes this thing. We agree, we have heard that in the morning. And again, we want to emphasize that, like, this is how we can really imagine the interactive system. There's an agent who decides on the policy. The environment is modeled as a Markov decision process, and it gives the agent a feedback of reward and states once the agent takes some action. And the goal is, as I said, like, this is the main point that we are going to repeat again and again, is maximizing this value function. Okay. So as Franz has already said, and this slide will be based on like how we can take the generalized policy iteration from discrete to continuous completely. Because what I believe, the components are really the same, just we find better like certain techniques to take them to continuous domain. So again, let's try to remember what are the components in here. I'll say there are three main components. One is rollouts, where you decide on a policy at every step. You play the policy for a certain amount of time. You collect the trajectories of state, action, reward, which is your observation from the environment. You use that to evaluate how good was your policy. So your goal is to try to estimate the value function of the policy. As you can see, if my policy at kth step was pi k, if I have started from a state called S0k, I want to estimate or compute this value function V pi k of S0k. And then once I know how good or bad it's this policy, I can decide to improve it. So which is called policy improvement, as Franz says, or policy optimization. We try to improve on the policy and get a pi k plus 1, which should probably give us better value. Okay. So we agree that these are the three components, right? We all are clear about that, why we need them, right? So if we are clear about it, like I wanted to give just a taxonomy of RL algorithms, because often I see this complaint from people that there's lots of RL algorithms. We don't know where to start, which one to put. So often, like I tried to make a rough taxonomy. Again, often things are a bit mixed in reality, but you can still divide them. Depending on the level of interaction with the environment, right? So how you interact with the environment to collect the data, collect the observation, you can divide it into two parts. One is online, one is offline. When it is online, when you sequentially learn while collecting the data by interacting with the environment, like real flavor of RL, right? You go, you take a decision, you interact with the environment, you get some observation back, you update your policy with that. Again, you take decision, take a policy, and then like you see some observation and you go on. So you collect data as you are learning also. And there is this offline RL where data can be collected before. By a behavioral policy nowadays with all this generative AI, you try to generate synthetic data before, or data from actual experiments. Like for example, if you want to now train, let's say, a clinical good policy or a good RL agent for clinical trials. You know, historically there has been lots of clinical trials. You have data for that. You know how people have done clinical trials, how people have put different medicines, which one works for which purpose, which one does not, right? And how long it takes for a medicine to work. If you know all this data, you can use them. You don't have to start an RL agent from scratch. You can use this offline data to create a model of the world or create a model of the good policy. And then on top of that, you start doing your experiments and go online. Okay. So this is typically the offline scenario. Then there are two other approaches. Like, so this was the level of interaction with the environment. Then the question is like, how do you want to find out your optimal policy? The first thing is like, okay, I want to find out the optimal policy, so I'll directly try to optimize and go for the policy itself. This philosophy is called the policy-based RL. So you evaluate every time a policy, you improve the policy and repeat. So which is why it is called the generalized policy iteration, as we have seen. But then there can be another approach in there that is called the value-based RL, which is sometimes also called off policy. Your goal is to find out first the optimal value function. You don't want to directly aim for the policy. You try to find out first the optimal value function, and then often take greedy policies on top of that, or even stochastic policies. You try to find out the policy from the optimal value function itself. And finally, the knowledge of the model. So what do you assume you know about the environment when you are trying to find out the policy? So first, like what we have seen in planning, if you want to really do dynamic programming, you assume the reward functions and the transition functions are known. And then on top of that, you want to find out the optimal policy, you want to plan well. But in reality, obviously, you don't know these reward and transition functions before. So what you try to do, you try to learn the model, or you want to use the model to do prediction or the model learning. So if you are coming from control community, you have heard of model predictive controls. If you are from RL, typically it is model based or model learning based RL. Okay. And in all these cases, you try to estimate models of reward and transition function from the data that you have collected either online or offline, and then use it further to find out your optimal policy. And finally, the last one is the model free, which is again, I like personally from my philosophy of RL, is you don't require any knowledge of RNP, you directly use the data to find out the optimal policy. So you say, I don't want to create a model of the world. I really want to take optimal decisions. I'll collect data. I'll go towards it directly. Okay. So we'll see these philosophies appearing again and again in different algorithms. So are we clear about this? Are you clear about this taxonomy and what we want to do? Yeah. So value-based RL, so we'll come to the value-based RL is the first part of the talk. So we'll come to that completely. And the online setting is the last part. So we'll start with offline value-based RL, then we'll go to online. Okay. So that will happen. And the second part of the talk will be mostly policy-based RL. Again, we'll start from offline and then we'll go more online. Okay. Any other question? All good? Okay. So now let us think about each of the components. So let us consider we have collected the data, we have done rollouts. Now we want to actually iteratively evaluate the policy itself. So as you have seen already, that actually how we iterate the policy is, as Franz says, by using the Bellman equation. And exactly I wanted to write it again because this is the kind of founding stone that we are going to leverage throughout our algorithm design, that basically you use this policy, or what we call, you apply the Bellman operator on the previous evaluation of your value function, you get the new value function, and you keep on doing that. And since, as like Franz said, and like as we know from before, these are called fixed point iterations. The idea is like if you start from a point, if you apply this Bellman operator, if you keep on applying, your distance to the true goes on decreasing. So this is a fixed point iteration algorithm. So that's the idea. Rather than trying to compute the optimal, what you do, you start from an initial point, you apply this Bellman operator, which is a contraction, which decreases the distance from the true over time. And if you keep on applying, actually you come closer to the true value itself. Okay. So it is like a self operator that if you keep on applying, you converge. So this idea is what we really use using the collected data or by rolling out the pi, depending on you are offline or online, to evaluate the goodness of a certain policy. Okay. And then the next part that we wanted to talk about, again, Franz did. I'm just trying to collect the components because these components are the things that will take us to continuous from discrete. These are the exact points that will change, and that's good enough. And then what we are doing, for example, as you asked, like what we do for value-based RL. So Q-value iteration is one example of value-based off-policy offline RL. What you try to do, you try to compute the Q table for each of the state action pairs. So for each of the state action pairs, you keep on applying this Bellman operator again and again, so that you try to reach the optimal Q value, which is in form of a table, which is a state cross action matrix. And then finally, once you get this Q table, you choose the policy as the greedy one that actually for every state gives you the maximum Q value, right? Do you agree on this? Is there anything unclear? Feel free to ask question. I like people who talk more, so don't worry. Yep. Okay, so all these methods under this can be applied for both stochastic and deterministic. Oh, no. Right now, here, we are not making any specific assumption. But most of the value-based RL typically tries to find out the optimal greedy policy. They try to estimate the value function and then calculate the greedy policy, as you will see most of the algorithms we see here. So finally, once you compute the Q table, you try to now predict or recommend the greedy policy as the best policy that you want to do. Okay. And here also, as you see, this formulation, as Franz said before, this is for deterministic policies. That's how typically we write it. But again, in policy gradients, we'll start to see where stochastic policies really matter. And using stochastic policies are very nice. You can do gradient descent, all the deep RL stuff you want to do. Okay. Okay. So are we good up to this? Cool. Yep.
Okay. Why we have model so we have why in this update we update only the action that we take with our eye, then we don't update for all the actions we can do it.
So that's a good question because what I was suspecting when I was writing this also, that when I was reading this also, not writing, then it wouldn't have been there, is you can do it for each state action. Rather, actually, when I was saying that you do this loop for each state action pair, I think this is a typo. I should have written it for S, A, S, A, S, A, basically, rather than actually writing it like this. Because, yeah, pi here is nothing because you really do a for loop over each state action.
Otherwise,
Yep.
Kind of
Not
place because you would update only the state action pair.
Yes.
That you actually abstain.
Yes. True. That's a good point, actually. Okay. Yeah, that's a good point. Well, I should, since I am doing anyway a loop over state action, I should have written it over state action, and yeah, it goes on. Okay. Yeah, that's a very good point. Thank you. So here, just the difference is like here we are applying the optimal Bellman operator because we care about getting the Q start, the optimal Q value. We are not applying any Bellman operator. So writing this pi thing as we have written for policy evaluation is meaningless here. And that's why you are right, like we are looping over all states here, but here we are looping over all state and actions. Okay, that was a very good.
The pi should be in the Q function inside the expectation over the next thing.
No, I think like this is fine. If I loop over all state action, I can put S and A here, and I can keep on applying the optimal Bellman operator on the Q of Q K minus SA and keep on applying it, right? So yeah, I think this is just a typo. This should be like S comma A everywhere. Okay, cool. So we are good. Yeah. If you randomly, all the Q values are 0. But then what is the optimal Q? Then? Yes. In the beginning, no. So you are updating. Here, there's no policy. That's what I said about the typo. This should become just S comma A, S comma A, S comma A. There is no policy in the beginning. And then you keep on applying it. Still, your question is valid. If I keep on seeing the rewards to be 0, this will stay there. But then the question is like, there's what's the optimal Q function? You should see something non-zero at some point to reach optimality, right? Yeah. Okay, we are good. Yep. Mm-hmm. Oh, so there's no belief. This is not POM repeat. We see everything, we evaluate everything, we get every observation. Yeah. So this B is basically, I didn't want to write A. So another index is B. Yes. Oh, no, that's not previous action. So you have a Q table, right? Imagine you start with basically like something like this. Okay. Let's try to imagine it better. So basically you start with a Q0, which is S cross A, right? Okay. So now you take every element, you apply the optimal Bellman operator like that, and you update it to a Q1, which is also S cross A, and you update this element first with your for loop, then one more, then one more. So there's no story of previous action here till now. So as I said, like this is completely off policy in here. Like we are not doing any action yet. Right? What we are doing is like we are using all these state action observations to just keep on updating the Q table. Okay. And then finally you are recommending. So there's nothing like complicated interactive is going on. Okay. So think of this like, to simply think of this, like think that I have given you lots of trajectories, right? And you want to find out using those trajectories, or here, for example, even it is better, you have the whole information of R and P. So for every S and A, you can call this function R, call this function P, and see what is the reward and what is the next state, right? And you keep on playing. Okay. So is this good? Yep.
Taxonomy, this will fall under the offline.
So this is off policy because first we are trying to calculate the Q and then going to pi. This can be, this is not offline and online because we have the full information, but this can be done in other ways, like if you already have a data set which covers the state action space enough. So rather than calling this reward and P, you really try to see from your data what are these values. Okay, so then it becomes an offline algorithm. Yeah. So anything else? Okay, good. So then we are good to go. And again, why does this stuff work? Because in the end, as I told you, like this is a contraction. So if you start from basically Q value, So if you look into qk and try to find out its distance from the optimal, you see like actually how you get qk is by applying the Bellman operator, the optimal Bellman operator on qk minus 1. And then you know that this stuff, this optimal Bellman operator is a gamma contraction. So basically your norm decreases by gamma from before. So it's like if you start from q0, you go to q1, then q2, then and slowly you keep on moving towards the q star. And then the other point that Son will talk about anyway much more in detail, but just I wanted to give like some hint on that, because you will see often in these queue updates, you have this kind of updates rather than the one we have seen before. What you do is like you keep 1 minus alpha component of the previous iterate that you had, and then you put alpha component of the next iterate. Okay. Why? Because like you know that Bellman operator is a contraction. So since alpha is less than 1, this stuff will still remain a contraction. So good, you are holding this property. But here you have one more thing, that if you actually want to estimate mean, you can estimate mean of anything in this way also. If you keep 1 minus alpha times the mu k minus 1, that is the previous iterate of mean you had, plus alpha times, again there's a factor, a scaling factor I am not adding, the new sample, then you can keep on adding new sample and calculate the mean of things over time, basically. Okay. So this is like anywhere you find mean, you can really go for this. Again, this formula again is not completely rigorous because there's a scale factor of n by n minus 1, but like Son will talk much more in detail, so I will not go in there. But this is again, all these are kind of stochastic approximation schemes in the end. Okay. So if you really want to do theory, start with how to find a good mean, and then you can go to Q values anyway. Okay. So now, what is the limitation of this type of things when we work in discrete state action spaces? That the first thing is the dynamic programming algorithms, they either require exact P and R or models that we have learned of P and R. And generally the GPI in discrete state action space, they suffer these things. Obviously discrete states, if you think of any control problem, most of the interesting one has continuous state. There's like discrete actions. Again, most of the continuous control thing, if you see they have continuous actions. Then the main property, which is interesting for machine learning people, that is generalization. Okay, there's an A missing, but it is still generalization. You can generalize over that. So like there's no generalization of this discrete state action type policies or algorithms. And we use only lookup tables. We don't learn functions that can generalize over representation. And then obviously it is computationally typically expensive to handle large state action space. Like if you have learned, like RL, let's say 10, 14 years ago, this is the main thing that your teacher would have said, like there's curse of dimensionality, good luck with that if you can ever apply in practice, right? So, but now we have come across a long way, and the idea is how we can make it work even if we don't have this exact lookup tables, if we don't have exact transition and reward function. And there comes the story of approximate reinforcement learning. The idea is, can we approximately learn good representations of the policy and its returns? So, or like, can we learn good representation of the transition and rewards so that that helps us to find a good policy, good enough policy pi. What is good, that will come to that later, but this is roughly the idea. And that is very machine learning a way of saying things that, okay, you do dynamic programming, etc. That's fine, that works perfectly. But I want to learn representations, which actually help me to generalize across tasks. And then that should give me a good enough policy that is close to the true optimal that you could have reached. And then the whole mathematical way of saying this, find a policy pi and a functional representation f, such that the performance loss, that is the difference between the optimal value function, true optimal value function of the MDP you are working on, and the one you are approximating with this functional representation, let's say neural network, linear regression, however you like it, is pretty close, as small as possible. Okay. Do we get what we want to do? Why we want? Okay. So no, F is some neural network that you use, or a linear regression, or a kernel, like whatever you want to use to approximate or learn this. Okay. It approximates the true optimal value function. Yes. So it approximates the value functions or represent them. So basically, again, the idea is like, since you are working in discrete things, only lookup tables, having tables like that, was enough, right? But here now you want to go to continuous spaces, you want to learn functions. And that's why learning a good representation of the function is important. Okay. So now typically the four key challenges, in my opinion, again, we can differ on that, in RL, in this setting, is basically first planning to large spaces where you really have the curse of dimensionality. Can you find a very succinct and nice representation of the information? And how to do that? We'll look into different functional approximation, and Guillaume will tell you more during tutorial how to choose different type of functional representations. Then the exploration exploitation trade-off. We saw a bit of glimpse of that in Bert's talk, like when you're trying to do the bandit, how much you should explore two arms to find out which arm is the optimal. You will see more of that in Son's talk on Q-learning, and later on in the optimism talk, we'll completely just talk about that. Okay. And then planning under incomplete information, how to mix the exploration and planning. Again, in the Q-learning, Son will talk a bit, and I'll talk about all these optimistic strategies later on. But these are for another day. Today, we'll look into these two problems. One is planning in large spaces and succinct representation of information. You have seen abstractions in there, but we'll take here a complete learning type of point of view, and we'll try to use neural networks or linear regression to learn them. So basically, we'll put parametric functions and try to learn them. Okay, so this is what roughly it is. Are you good with this? Any question? No? So no, not only policy. So in this part, in the first part, we'll talk about if you write value function as a parametric function, like a neural network, like a linear regression, like anything parametric function, right? In the next one, when we'll go for policy-based method, we'll talk about how to write policy as a parametric. It can be, again, a neural network, Gaussian. We'll see, like there are lots of examples. And then we go on. So for both cases, you can put different functional representations while learning. Okay, any other question? Okay, so now we'll go for the first part where we'll look into the value-based methods and how to use functional approximation or representations in RL, specifically in this case. And the whole motivation, as we have said, going from discrete to continuous states, going from dynamic programming to more learning type of strategies. Okay. So as you have seen in France's talk, this is from his slide, you are trying to evaluate this policy in the small grid world, right? You are trying to reach this goal. Now I said, like, okay, I don't like these boxes. I want to go more granular for my planning, and I increase the number of boxes to this. And the thing is, the Q table you have learned there does not work here. It is not generalizable. Just this small change makes it completely fail, right? So no generalization across discretizations. And now you come up to mountain car, and which is a continuous problem, and this is the value landscape of that. And this is due to Sean's book, who did the simulation, painfully, and try to show you actually how with different positions and velocities your value function actually change. So depending on where you start, your value function has a very different landscape. And this is not a table. You can clearly see this is a nonlinear function, right? And you want to really learn it. So now you don't want to learn the Q values, but them as a function of state and action. Okay. So we are clear? Okay. So then the question is, exactly computing a Q function across continuous state action space while looking into trajectories, just trajectories coming out of the environment, is impossible, right? So it's not possible to exactly compute that because it is expectation of sum of return till infinite horizon, right? First thing, like, you don't have infinite time to go infinite horizon, do that simulation, and again, computing the expectation exactly is too hard. You need too many samples. So basically, even doing this simulation like this takes quite a bit of time that you don't want to do if you just want to find the optimal policy. So the question is, can we approximately learn good representation of transition and rewards or directly the Q value function and use them to find out a good policy? So we divide this question into three questions. First one is, exactly, can we approximately learn generalizable and accurate representation of Q values? First, let's look into this. Can we find out good representations of Q values, and how? So the first thing you have seen that Q function computation was what? It was applying on qk minus 1 the optimal Bellman operator, right? So we wanted to apply on qk minus 1 the optimal Bellman operator to get a qk. That was your principle that we learned from dynamic programming, right? Or from Bellman itself, the Bellman equation. Now what I am saying that, okay, maybe I don't know this qk, I cannot calculate them, but still the operator stands. And if I apply that on a parametric equation of q, let's say q is now a parametric function with parameter theta, and it is a function of s and a, still I can apply this operator, right? So how would it look? Rather than putting qk minus 1 or qk here, I'll put q theta at both places, and I apply this equation. Fine. Now, you want to estimate the parameter. Whenever a parameter comes into scene, you want to estimate it, right? You want to learn it. And the whole point is, you now sample trajectories of state, action, next state, and reward from the actual environment, and turn this finding out theta into a regression problem, right? That's classically what we do. Like, we take data, we have a functional form, we know both the side, y and f of x. We try to minimize the loss between y and f of x, right? So this was your left-hand side. This was your right-hand side. You write a square loss between them, and you try to find out the theta that minimizes the loss, right? Is it fine? Think of it. So the first step was, like, we took the optimal Bellman operator that we apply iteratively, but rather than applying it on a table, we now apply it on a parametric function with a parameter theta. Then, to learn theta, we collect trajectories from the environment and apply a regression. We try to minimize the least square error. Fine? Okay. If we do that, we can get a good theta, a good parametric representation of the q value itself, right? Do you agree? Any question? Yeah. Q on the left-hand side, right now it is not an update, but it should be an update. You are right, right? I wanted to find out optimal Q. I know that optimal Q can be written as written as optimal Q is equal to optimal Bellman operator applied on optimal Q. I wrote both of them with theta. I just apply regression and try to learn that, right? So I say, like, I don't want to do all this dynamic programming, iterative stuff. I just want to learn the parameter. Because here I am turning the problem into a learning problem. But then your point comes true, like, so here the fallacy is you have q theta here, you have q theta here. You want to evaluate them, obviously, otherwise, like, if you cannot evaluate, how you can take a max, basically, right? So literally doing this is not exactly possible, right? Because you have a q theta, here you want to take q theta max, you have to have something static. Your target is moving, your data is moving. So both y and x are moving. You have to fix one part of it, right? If you want to do regression properly. And there comes the next point. Forget about this. There comes the next point, that what to do, what would be the target in here? Like, what would be a good way to generate data to directly learn the optimal Q function? Because unlike the standard schemes, we have only limited access to the target that we want to reach. We have just a bunch of trajectories. And if you try to really find out the Q theta star directly from that, either you have to have extensive trajectories that covers the whole space and includes also trajectories from the optimal policy. Otherwise, you can just learn something random, right? So here the point is, you can leverage something here. So we remember that there is one good property of Q values if you apply through Bellman operator, that they are contraction, right? Over the time, they go closer and closer to Q star itself. So the question is, if I really want to turn this iterative, let's call this theta k plus 1. Let's fix a theta k in there, and let's keep on applying this again and again, right? Because in the end, what I'm trying to approximate is the optimal Bellman operator. I know if I apply the optimal Bellman operator on qk, I get qk plus 1, and it goes on to be a contraction. So what I do is, like, when I'm applying this Bellman operator, I'm putting a qk there. And here the theta k I'm trying to find out is the theta of the next step. So what I do is exactly this, that I take motivation from the GPI, I put a theta k in here. right? Because on that thing, we are putting up the optimal Bellman operator, and we are trying to estimate the next one, which is the theta k plus 1. Think of it a bit. So first thing, again, if we go back, we knew that we can find out by applying the optimal Bellman operator again and again iteratively. And we know for the optimal one, the Q star itself is the optimal Bellman operator with the Q. And then what you want to do, you turn this into a regression problem. So what you do is like you use Q on both sides, try to find out the parameter that optimizes it much. Now you don't want to like use too many crazy amount of data. You rather want to iterate and leverage your structure that you know, and you don't want both the target and both the target and the thing that you are estimating moving at the same time, right? So to decouple them, what you do, you leverage the fixed point property of the Bellman operator itself. You keep the thing on which you apply the Bellman operator as theta k, and then on the other side, you try to estimate the theta k plus 1. Okay? Yeah, ask if you have any question, don't worry. Yes, yes, perfect, yeah. Are you good? So now we have an iterative scheme. So for steps up k equal to 1, 2, 3, and so on, you keep on applying this again and again till you get happy with your theta k. And now the question is, let us assume like you have found out a good theta k, you approximated the Q function well. Now you in the end wanted to find out an optimal policy. What is the optimal policy in here? What would be the good way to find out the good policy from here? The answer is very simple, up. Yeah. So basically, if this Q hat in the end becomes a good approximation of the Q star, then basically apply the greedy policy on top of it. And that's the policy you recommend. So this part is pretty easy, but we still are in discrete action. Just remember that we are still saying all these things for discrete action. The question is, why would it work? Like, think of it. We'll get the answer in a bit, but like, think of it, and then I'll ask again, like, why would it work? Why do you think, like, after doing all this learning and approximation, still I am saying the greedy policy is a good way to go? Okay. So now we have seen 3 components. The first component is sample trajectories and solve the regression problem to estimate a good theta star. Okay, where you use basically Bellman operator, optimal Bellman operator applied on Q as your target, and then the Q theta is the thing that you want to estimate, or its parameter is the thing that you want to estimate. Now, as a target, you want to use Q theta k minus 1 as the target function, because you know there's this good property that if you again and again keep on applying the Bellman operator, things contract. And then the last point is when you're happy with your approximation, you use just the greedy policy on top of that, right? And that gives us exactly the first generalization of the Q iteration that we have seen. So this is called the fitted Q iteration. And the idea of fitted Q iteration is simply this. If you now try to think of why I was emphasizing on 3 points, rollouts, evaluation, and then final policy improvement or policy recommendation, right? So here if we see at every episode, we are taking an initial sampling distribution, let's say initial state distribution and an initial policy, or you can think you have a data set, or you could think like you have a simulator from which you can sample lots of state actions. You initially do that. You initially sample lots of state and action, and then you apply the transition function on that to get next states. You apply the reward function on that to get a sample of the reward, and this is your data set, right? You start with this data set of S, A, S prime, and R, right? You generate lots of independent samples of that. But your regression problem was not on that data set. It was a bit something more than that. Like that was creating this yi's. So yi's are what? Like their ri plus gamma times maximum of this q value, but where I am using the previous estimate of the q function to compute this maximum of q value for each s prime and b. Okay? Fine. And this y and the s comma a, they together create your data set. So now whatever you are doing with rollout, you have a proxy of that in these steps, right? You have created a data set. Now, using this data set, you solve this regression problem, and you get your next Q value or the parameter of the next Q value. And then you keep on going and going till you are happy and you say, okay, now I'll use this Q function to recommend the policy, and this policy is argmax, just the greedy policy on top of this, right? We are fine. So yeah, tell me if you have any question, anything. Okay, so what's the time? Okay, we are doing good. So now I have one question before we move on. Why do you think this YI is like this way of generating data is a good way, or like this can give you a good unbiased estimator or a good regression in the end? Like this YI, so originally, again, I'll try to remind you, maybe I'll write it here so that we remember it always, because that's the whole purpose of it, that we have this Q theta K plus 1 that we want to find out. And we said that is basically this optimal Bellman operator applied on this thing, right? And I said, like, we want to do this regression rather than applying this Bellman operator per state and action to go here, to go to this estimate. Now I am saying that this is a good way to generate data. You generate lots of independent samples of state action, take one step forward, just one step forward with each one of them, and then you calculate the optimal Bellman function out of it, and that works as a good Y. And whereas your state actions are good X, right? So why this Y is a good Y? Okay, the question is like initially in the regression, my two parts are this, right? This is the data part, and this is the target part. I am saying for this data part, for the Y, I will use this Ri plus gamma times maximum of B, this thing, right? I'm not using exactly this Bellman thing, right? I'm generating lots of data that I am claiming is a good way to go there, right? Why this would be good? Or when, like, let's forget why. Like, when do you think this yi is a good representative of what I'm trying to do? Is a good representative of the outcome? That's if enough data, then the regression will work well. But even if I have, say, let's say like 2 data points even, like how do I say that this regression is just going correct? Like it makes sense in expectation, let's say. Yeah. Yeah. No. Yeah. Yes. This is yes. No, just wanted to, because I saw like we have time, so let's have some fun, basically. Yeah. No, that's a very complicated answer to something. Think about regression. Uh, yes. So here, exactly. That's for sure. That's for sure. No, that is mitigated by this fact that you are collecting enough independent samples from the whole state action space. So yeah, so one, then we go. Yeah. No, right now I don't care about the functional form. Yeah, that's the slide I skipped. Guillaume will talk about that. Yeah. So then. Yes, that's a good point. But the thing is, like, let's say, like, when do you think a data that you use for regression is a good data? Uh, okay, okay, we are going close. Anything else? Exactly. So that's the whole answer to it. Basically, the whole idea is we can use yi for that because in the end, expectation of yi given s and a for any y is exactly this thing you are applying. So if your data is in expectation not representative of the true thing, then how can you do regression? Yep.
It's like the learning estimate, right? So we know that, for example, when we choose learning, that's Monte Carlo, we know that we are adding bias.
So this is a bit different than TD learning. TD learning is a bit different from here. So here we are not saying that we want to find out the temporal difference or optimize on that. No, the idea is that I have this equation that I know this is the optimal Bellman operator that you put. That's why you take the maximum and take one more reward from there, right? So this data is representative of the right-hand side, and the Q theta that you are trying to estimate, let's say, you don't know it right now, is basically the representative of the other side where you have this f of theta, right? So that's all, I think. This I really mean rho pi 0. There's a point, and yeah, that's a good point. Okay, so since you have asked it anyway, so we can say this line 4 and 5. So there's some choices among people. Okay, so 4 and 5, like some people really like to resample at every episode. There's a good reason to that because then you don't carry the bias of the past in there, and like you resample and like you are doing regression at every step again and again. But this is too costly, so that's why people often do this step 4 and 5 before they store this data, and then they keep on doing regression on top of this. Because here you are going or converging not due to the data. You're converging because you're doing this regression through the optimal Bellman operator. Okay. So the data, you can keep it same, like what in deep learning, deep reinforcement learning people nowadays call the replay buffer, basically, right? Yeah. So this is the offline data that you collect, keep, and you say like, okay, this is always I can use. Yeah. Yeah.
There, we're only going to find the maximum, the best way of behaving of the things that we actually visit.
Yep.
So if we don't visit what, I mean, I think people have mentioned this. A is a deterministic
Yep.
policy. So
Yep.
So do we have to add?
Yes. Obviously, like there has to be exploration in there. Again, like as I said, for the Q learning part, which is a bit more different than this, like, and Sean will talk about how exploration happens in there. And in the optimism talk, like we'll really talk about how to do optimism, basically exploration, exploitation trade-off at different steps continuously. Yeah. Here, the assumption is you have collected diverse enough data that covers your state and action good enough, so you can learn a Q function. Yes. Even like you can think of rho is basically the main thing, the initial state distribution. You collect lots of states, and pi 0 is, let's say, most of the cases, the uniform random policy from each state you take and collect. Yeah. Yes. Exactly. And this is really an offline of like value function based approach, right? As you have asked, like, because you are collecting the data before. Okay. So are we good? Yeah. Yep. Yes. So that's the exact next one. So why does it work? The question is the first question even before that is like why I asked. Oh, I have shown you. Why does the greedy work? Yeah, I forgot that question. Why does greedy work? Like why finally taking this greedy is good? Yes? Yes, because that's the greedy deterministic policy, you know that works. But the thing is like you are applying it on the function approximation. The question is like, does it still preserve the contraction, right? Does it still take you closer to the true? But the intuition is correct because you know you are searching for a greedy deterministic policy. So you are going for this. Okay, the answer to that is that's true. If you really like take the optimal value function and then you apply the greedy policy on the value function you have estimated till now with theta k, if you apply like the greedy policy in there, actually you can show you can go up to 2 gamma divided by 1 minus gamma, which is something very small times the learning error that you incurred. Basically, this is the learning error without applying the pi. Okay. So this is what you get, and you see basically from performance loss, you go to learning error. Okay. So then we can focus only solely on learning. Are we good? Gamma was the discount factor in your value function. Yeah. Are we good? Okay. Next question is what happens with this? So that was the question Thomas asked is like what to do next. Now from learning error, you try to write this analysis. Now you put up the learning theory hat and try to write this learning error into two parts. One is the estimation error and another one is the approximation error. And why these two things? Because there are two phenomena that happens when you try to analyze this. One, you have to collect enough sample, so you cover the space enough, so you have enough information to estimate. So for example, even forget about value function. If you wanted to estimate mean of something, you have to collect enough from the distribution so that the average you are calculating is very close to the true one, right? So this is the part where whether you are collecting enough sample depending on the structure of your space that you go close to the true thing that you want to estimate, the true statistics, right? So this is the estimation part, and that depends on the complexity of the class, the coverage that the samples collected, and that is exactly what depends on this portion. That dictates how much n that I have to collect typically, right? And then the next part is the approximation error. How good is the function class that you are using to approximate the optimal value function? And that's where your choice is, like whether you, for a problem, linear is enough, maybe some from other problem, like you want to go for neural networks. It really depends, depending on your environment and policy's complexity, what is a good functional representation, so that even your empirical one and the one that you are representing with this function are close enough. You are not losing much information because you are using a parametric function to estimate it, right? So these are the two things that you try to bound, and these are called estimation error and approximation errors. And this started around, like, at least in my knowledge, around this works around 2012. And then people have done a huge amount of work. If you go to the RL theory statistical part, like, yeah, this is a kind of your bread and butter for your career, basically. So you try to analyze them. So are we good? Okay. So now we have learned something, but everything has a fault, and like this also does. That's why we develop new algorithms. So what are the problems in there? First thing, FQI is an offline RL algorithm. So you already collect the data, you really trust on the diversity and the coverage of the data, and then you learn to do regression. FQI loops over all possible action to get the next best action because you are calculating the greedy policy. So here, if you have continuous action, for example, or very large action space, things are a bit too costly. This thing encounters also instability because the target depends on theta. This would be theta k minus 1 in this case. So basically, your target depends on the next state, and like you are trying to estimate something on the previous state. So there's a temporal coupling between the target that you fixed and the other part. So this causes the instability in there, like this causes high variance and instability in your regression. And the other thing is, like, here we have talked about the collecting data at every episode and forget them in the next one. But again, as we have seen in the question, you can often create this replay buffer and use it throughout. So now you find out like something that probably you have heard of in this world of deep neural networks is DQNs, right? How many of you have ever heard of DQNs? Okay, quite a few. Okay, so then I can skip this slide. So yeah. So in this case, like what you try to do first is try to take this offline RL algorithm to an online one, and you try to collect data over time while keeping the previous data collected as a replay buffer and keep on using them over so that you don't become very sample inefficient. Then you try to just go for one forward pass to get all this theta q theta k, and again you use a target network for this part, as like we have already seen during questions, to ensure stability, and again replay buffer to reuse the data. So I'll not go into this, and the exploration part that you are asking about is like that's why people use typically epsilon greedy exploration in here, so that you cover the state space enough, you still have exploration. But again, these components we have not explained, so we'll not go in much detail, but you can look into the slide and let me know like during tutorial or after, like if you have any question. So now, before going into that, like roughly we are good with the schematic of FQI. What are the problems? What people try to do to mitigate that roughly? Like obviously I didn't go through every step of DQN, but you got the ideas? Any question? Ah, so that's the part where basically you see like at one side, if you really have seen what you are trying to estimate is this, Q of ST comma A, right? On the other side, what you are fixing or applying the Bellman operator on is next state, ST plus 1 comma A, right? So, okay, let's go back and take a look at this thing. At this side, you had S comma A. At this side, you had S prime comma A, right? So this thing is generated from there. So there's a coupling between them through the transition function, right? And that causes high variance in your total estimation or regression problems. So that's why what you try to do, you try to decouple them. You put another network to estimate this, so that you use the same data, but their estimator decouples them from each other, and then you keep on applying the same property. So that's the thing that in DQN people call the target network. Okay. This is the intuition. I didn't give you the mathematical analysis, so you have to just have a belief, like you can, yeah, so no guarantee further on that. But yeah, that's the roughly the idea. That often like, so this is a like classic way of handling confounding or like exogenous data. If you have two things which are dependent, often you put a third thing before that helps you to estimate this other thing, and then you do regression or variance calculation, whatever you want. You don't use directly the variable itself because they are correlated, but you use something previous to predict the variable, and then use the predicted thing to do regression, all the statistical stuff, basically. So these kind of things are very common, like if you go for exogenous data, where data has unobserved part that makes it correlated, basically. So this is a very classic or interesting trick from there. Okay, but still, the story doesn't end, and like Aditya really wanted me to talk about deadly triad, basically. So we have this slide. So if we use FQI or DQN with experience replay, we face the deadly triads of RL, right? And what are the deadly triads of RL? Like here you are using function approximation, some neural network, some linear regression or something. For Q, you are bootstrapping. You are using this max of A Q theta SA, which is really a really an outcome of Q theta itself to construct the target data. And then you are doing off-policy learning. Since you don't want to become sample hungry, you are not sampling again and again. You are using data collected from the previous episodes to do your regression. And these three things together, if they appear, you can create counterexamples where you can show that things are not converging anymore. Things can diverge. Due to different statistical reasons, you can show like small counterexamples where your final outcomes diverge. But I'm always like not very clear, and I think most of the people are not very clear why this is happening, because in most of the practical cases, it does not appear. And the question is whether that's a silver lining for us or a very myopic situation. We have bad algorithms where we don't know what to do, or a bad theory that we don't know how to explain. Is that empirically we rarely see this appearing? Well, only just some explosions in initial values, and then they come down. So this is called the soft divergence, just maximum that with small amount of data, but nothing more. And maybe like in practical cases, we never see all this, weird degenerate examples. Maybe in real life, everything is stochastic. If you do a stochastic analysis, life is good, right? Yeah. Yes. Yeah. Yep. Yeah. Yeah. No, this thing really like we don't have a. That's why a good theoretical implication or reasoning like why it would ever happen. So either we need a better theory or like we are already happy and good, as RL people. So yeah, the question is which way is the final way. So yeah, so I agree with like Son's idea, but yeah, we don't know a good answer. Yeah, yeah, understanding. Yeah. So and yeah. Okay, so this is like if you are searching for open problem or something to do, or if you don't have anything to do, like this is a good question. Okay, so now we can reach the intermediate summary that we leverage the Bellman operator's contraction to iteratively approximate the optimal Q function. We turn the Q function approximation or Q function learning into this regression problem where we keep on iterating using the previous iterate of Q value and solve a regression to get the next parameter value. We have to use a good data generating policy that covers the state action space, or at least like reuse the old data smartly. This part we have not talked about, but like you can look into the literature for this, or we can give you material, and then use the greedy policy once your estimate is done. Okay, so that's simply the most of the idea. Okay, so are we good till this? Then we'll move to the final part. Okay, any question? Yes. Uh, what do you mean by tabular policy? The state is continuous. State can be continuous. Oh, so you think of continuous state and discrete actions. So for all the state actions, you have created a function that you give an input and a state action gives you an output Q value. And now you want to choose for every state the action that maximizes the Q, right? Yeah, that you can evaluate. Okay. So are we good? Okay. So then the next part of the story. So we have looked into the values and stuff. It's fine, but you can ask like, and often people have asked, I wanted to get the optimal policy. Why would I care about, this big table or function basically? I want to get my policy done. So what people try to do is from dynamic programming, now you want to go for directly parametric policy optimization. So you turn your policy now into a parametric function and you try to find out its optimal parameter. So the first thing, as I said, represent the probability distribution over actions as a stochastic policy, like a parametric one. And then you can go for different parameterization. This part Guillaume will not talk about, so I will. So like in discrete action, you take this pi theta of taking an action A from a state S as directly as a probability value, theta of SA, such that the sum of those probabilities are 1 and the probabilities are non-negative, right? They are greater than equal to 0. These are just probability values, but never use that. So then the next thing that people use is the log linear policy, where you say basically my policy has now this form, that is theta transpose some feature dependent on A and S, and then you exponentiate it, right? The exponentiation like is something very common, as you can see. We'll see why we go typically for exponentiates. Okay. First thing is it keeps it obviously non-negative, and rest it is easy to normalize, and you get the sum to be 1, obviously, because policy is in the inner distribution, you have to sum it to 1, right? So this is good, and then you say like, okay, I don't like linear stuff, you can put a neural network, like a policy network as people call it, and really again train, right? Okay, and now if you have continuous actions, then people go for this type of policies. One is the Gaussian one, another one is the beta one, if you specifically have bounded actions, because Gaussian has an infinite support. Here you have two things that you want to estimate, that is the mean of the Gaussian and the variance of the Gaussian. And you can put 1, 2 neural networks or like linear layers just to estimate these things from data. Okay. And again, similarly, if you have a beta distribution, you cannot work only with the action itself as the random variable. You have to recenter it by using the maximum range of the action Amax in this way. And then you use on top of that alpha and beta as the parameter of the beta distribution. And again, you use two neural networks or linear layers to estimate the parameters, alpha theta and beta theta. Okay. Is it good? Okay. So now in one side we have this kind of exponentiated distributions, and in another side we have also exponentiated distribution, because most of the cases in practice you come back to exponential families, right? Which are good. You can do statistics, you can do optimization, you are very happy. So now the next part, once you have represented it using a parametric family, you want to do optimization. So the idea is you want to find out the theta star that really maximizes this total expected value function, where you assume the first initial state was sampled from initial state distribution, right? Are you good? Okay. So now the question is how to do that. So the first thing is you try to go analytical, you try to find out a solution if you can find one. But the problem is often this v pi theta, expectation of b phi theta, S naught is non-concave in theta. So you don't have one closed form expression. So probably, yeah, it's not as good as, like all the Bellman equation and things we have seen. Very nice stuff. So what you do, you take your deep RL hat and you say like, okay, when I don't know how to optimize, I do gradient descent, right? So you start with a theta k or theta 0, and then you take the gradient of this thing. So for now on, we'll write this expectation of the value function as j of this pi theta, because that's what we are interested in. And this is how typically in control also we write gains. So we now take the gradient of this j and keep on applying it again and again. But the story does not end here. That's why we have this bunch of policy gradient algorithms. And that algorithm, what is the issue? That j pi of theta cannot be computed exactly, because this is the expected value function with expectation over initial state distribution. It is very hard to compute that exactly. So what you need is a stochastic approximation of the gradient, right? Now the whole literature of policy gradient is how to find a good stochastic approximation of this stuff. Okay. So are we clear about the philosophy of the algorithm design, right? Okay. If we are, then the first thing, let's try to write the gradient and see how we can evaluate this. So the gradient has this thing that it has an expectation over tau, z of tau, and the summation over the gradient of log of the policy. And now you see like why exponential was everywhere, right? If you take log, it becomes directly the equation, you differentiate the stuff inside, right? And this is the famous policy gradient theorem of Williams from 92. And now what are the components? Let's go through them one by one. Tau, here is a trajectory that is generated by applying this policy pi theta on the MDP with this transition function P, and where the initial state distribution was rho, right? So with this probability distribution, you keep on generating trajectories of SA, 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 and so on. Okay? Fine. And then what is Z of pi? Z of tau. Z of tau is the return of this trajectory. That is the sum of discounted reward if you have applied this trajectory and collected all the rewards, right? Fine. So basically, you take one MDP, you apply the policy pi theta on. So you initially sample an initial state S naught, you apply the policy pi theta, and you keep on seeing what happens. You just roll out, right? And from that rollout, you collect reward, and this Z tau is just discounted sum of that. So it has nothing to do with, nothing to mess with your optimization problem. That's very good. And then this is the only part where the gradient lives on. And in this part, you see this gradient of log of theta often can be written as gradient of log of pi theta can be written as gradient of pi theta divided by pi theta, which is often called the score function, and exists for most of the differentiable parametric families of policies. For example, if you think of the log linear policy that we are talking about, this gradient looks exactly like phi of A's, that's the feature corresponding to state and action, minus expectation of this phi of A's. Okay, so this is kind of basically a deviation of the feature from its expected value. And that's pretty simple to evaluate, right? That you can evaluate really from rollouts directly, because you can calculate this expectation if you have rolled out enough, and you can calculate this deviation from the expectation, right? This is simply calculating the average if you have rolled out using a policy. So we are good? Do we understand all parts of this theorem? Okay, because rest of like 20, 30 years, whatever we have seen, or even, 30 years, I think, 30 years, whatever we have seen, is playing around with this equation. So the first algorithm in this way was the reinforce. The idea was like generate a trajectory at every step. Okay, this should be small k, using the policy pi theta k, and then estimate the gradient like this, that you just use the trajectory's discounted reward as an estimator of z tau. And here you directly use basically the policy's gradient, which you can evaluate again using only the trajectory, the things you have collected. And that's all. That's your estimate of the gradient. And you apply this while doing the gradient ascent, and you keep on, right? And the good thing about it, like you can prove this can be an unbiased estimator just if you have one full length trajectory. And that is enough to give you an unbiased estimate. Okay. And that's very good, right? So you don't have to roll out multiple times, etc. You have from the beginning an unbiased estimate. It's not like after getting a lot of data, you become unbiased. So this was the first algorithm. So that is the good part. But the bad part, and that actually still troubles the most of the policy gradient methods, is the high variance. And why? Because this z tau, which is can be evaluated independently, and this gradient can be evaluated independently, very cool, very nice, but they have correlation. When you evaluate them like this and try to calculate one single expectation out of that, often this again, that was the same idea as we have seen for QST plus 1 and QST being correlated, right? On both sides. Again, if things are correlated, if you apply them together without a correlation correction, often they lead to high variance. Okay. And this is a standard issue of policy gradient. So now people have said like, okay, I don't have the luxury to have infinite length trajectories. I don't want to compute this sum like separately, this sum separately. Can I use something, can I leverage the Markovianity a bit more during the estimation? The answer is yes. And the answer is very simple. Here you see one thing, that the reward you get before the time t does not depend on pi theta t, right? Only the reward you get after time t depends on the pi theta applied on st, right? So you can take in this sum, saying the only sum that you care about is the t here, and then you want to take the sum of rewards that is only appearing after the small t. And you use it with the AT, you see? Like you are just now using the t, the time of the policy, as the dictating time, and you are saying, since I know everything before that is independent, I'll take only the sum from the small t onwards. And what is this thing? This is exactly the gamma to the power t times the q value of STAT, right? So basically, if you have a scheme that can evaluate the q value of a function of a policy, then you can really plug in this q value estimate in here, and you can evaluate this stuff, right? So this is called basically the q value function version of the, or the action value function version of the policy gradient theorem. So this is the second version. And the one, if you now go and try to apply from stable baseline or whatever the standard algorithms, what you see is this version. The question is like, obviously it has a high variance, can we decrease the variance? And the point was like, okay, let's subtract something from that so that the thing appears scaled down and the variance appears scaled down also. What to subtract? Since the ST is something determining here, so we cannot remove ST. What we do is for every q value, we remove a b of ST from there. B can be any baseline function till it satisfies this, that its expectation with the gradient while multiplied with the gradient is 0. Basically, then subtracting this term does not mean anything in terms of expectation, right? Because this function with this gradient has an expectation 0. So then subtracting that from this equation does not change the equation at all. Just decreases the variance, right? Are you good? Okay. Now the question is, what is a good BST? Like, what would you choose? What would be a good baseline that, being keep your RL bias on and try to think what would be the BST that you want to put. Yeah. So, like typical very good RL people, you put V as your baseline function. And once you put the V as the baseline function, you see this is exactly the difference between the Q value at state ST with action AT minus the value function for the ST. And this is exactly is known as the advantage function, right? So this is the version, if you go to most of the deep learning implementation, this is the version you will see being applied in there. Okay, so this is, again, if we think of this gradient, there is sum of gamma t, the advantage function of the corresponding state action, times the gradient of log of policy at that action and state, right? So are we fine with this, how we are reaching there? Any question? Yep. You can use that. The question is like, right now I cannot imagine the expression out of my head. Is the expectation 0? That we have to ensure there. Because this is the only constraint we have. Yeah. Yes, sure. No, I understand where you're like stating that from, but yeah. But I'm trying to think that if I just think of advantage function as difference between counterfactual actions value, state action values, then can I play the same trick that the baseline, whatever I'm subtracting, gives me this expectation 0 condition? Because yeah, if that happens, then for sure we can write this. Yeah. Okay. So are we good? Any other question? Yep.
So B is a good choice for the baseline, but is it the best choice?
No. Yes. Yes. So basically, again, if you put the statistician hat, the way is you try to calculate the variance of this estimator. You see how this depends on B. You differentiate, make that smallest, and choose that B basically. Yep. Yes. So yeah, you know now the resource, basically the reference. Yeah. So yeah, so that's how you can choose the the B. Now, once we have these 3 versions, now if you go and look into different policy gradient theorems, there are different ways of estimating them, basically. The advantage and the gradient, and that's all. Then one specific algorithm that I really wanted to talk about is this natural policy gradient algorithms. So the point is, like previously we are just doing a gradient estimate in here and doing a gradient ascent, right? Now we are saying that we want to be curvature aware while doing that. So basically we covariance calibrate this thing. So this is the pseudo inverse of the covariance of the gradient. Okay. So basically I calibrate with the curvature of this log policy space. Or sometimes if you are interested in information theory, it is the Fisher information matrix of that. And you use this, use pseudo inverse of that to take your gradient step now. And this is called the natural policy gradient. Again, if you are coming from optimization point of view, like this will be very familiar. This is like ever if you design first order optimizer, next thing is like you really design this for your problem. Then the final one, finally, we see, okay, do we agree before that? Like, do you see why we do that? Right? So you have seen optimization systems like where often you apply Hessian inverse and then take the gradient multiplied with that and you keep on doing that, right? So basically this is a way of saying rather than just using the first order information, you use the second order one or the curvature and you keep on going, right? And that's why, maybe probably that's why, I don't know. Natural policy gradient is called natural, maybe, I don't know. Yeah, so this is the purpose of this one, but this actually gives us a very good family of algorithms. And something that you know, like some different types of proximal estimators are now used, or optimizers are now used to provide algorithms like PPO, TRPO, and so on, what is the idea? That if we really look into this formulation, this update step, you can think of this update step like doing theta, finding out theta k plus 1 that maximizes this j pi theta. That's fine. That was our goal. But with another constraint, that the KL of the final distribution of trajectories induced by theta k and any other theta that we want to optimize over should stay below a certain level epsilon. And specifically, if you are used to with the expression of KL, that often people use the second order approximation of the KL, which looks like theta minus theta k transpose sigma at theta k, theta minus theta k. Okay. So if you really use this constraint, put it here, put a Lagrangian and try to find out the first order approximation of this or first order step of this, you really find out exactly this one. Okay. So if you put this constraint, do a Lagrangian optimization, really try to find out what is the first order step corresponding to that, you see this sigma theta k appears as a pseudo inverse or an inverse if it is a full rank, and then you can keep on updating using this. Okay. So this says that rather than, and we know from practice that rather than doing the classical policy gradient, this natural policy gradient really works better, gives a better convergence analysis, better stability analysis. Now the question was, that means the general trick that you should not go in any step too far from the theta k you have, right? Is a good idea to go. You should take small steps in your policy space to go towards the optimal, not too far at once. And that gave us all the famous algorithms most of the people know of, the TRPO in 2015 and PPO in 2017. The whole idea was literally transferring this, but without the first order approximation or the second order approximation of the KL. You just put the advantage function in there. You know that you want to generate the data from theta k, but you want to optimize over pi theta, so you directly put pi theta in the numerator and the pi theta k in the denominator. So when you take the expectation, they really cancel, because this is the thing you can really evaluate. You can really use the policy of the previous step to generate the data, and then you maximize this expected value function such that the KL between the pi theta that you want to calculate and the pi theta k, that should be as small as possible. Okay, should be less than a certain threshold. And now if you remove all these things, try to do the maths a bit better, you can show that can be achieved by basically saying this ratio up there, if that stays very close to 1, it should not be like more than 1 plus delta or 1 minus delta. So if you clip this ratio not to change too much at every step, and then again still you optimize over theta, that is another way of ensuring that you stay proximal to your previous update, right? So this says basically your ratio cannot change too much. So your theta, even if you try to do the max, should not go too far from theta. And this is another way of ensuring proximity. And like if you are interested in optimization, if you know all these proximal operators, you can put a few of your own and see like whether it works. You have one more. So yeah. So this is how roughly all these algorithms are designed. But typically the idea that using proximal operator to like control the step size, the jump you take with the policy update, is a good way to stably induce or stably go towards the optimal policy as an optimization procedure. Okay. So now have all these things. Now the final question is, why does this thing work? The answer is this. This thing will work if we can show around pi theta star, this is something like a concave-like function. If that is the case, then our gradient optimizations work, we know. And if it is concave-like, then the pi theta you achieve and the pi theta star, their value functions differ by norm of their gradient. We know this again. There's no RL here. This is known from optimization techniques. And then the other question is like, if you now have enough coverage of your state action space with the sample data or the sampling distribution, and if you have designed an unbiased estimator, like we have talked about in reinforce, then you can prove a pack guarantee on the gradient that you are estimating. And if you have both of them together, then you can show basically the policy gradient works. But it is not just these two lines. It was obviously much more complicated than this, but these are the two ideas that actually formed all these works and the improvements on that. And you can really read like these three papers, like I really enjoyed them. So you can really try to see like how optimality, approximation, all these things matter in policy gradients. Okay, so we have found out another family of algorithm, the policy-based one. But then the whole point is like hard to choose the step size. If you jump too much, you go too far away, you go unstable. So that's why you use clipping, you use this proximal operator, and sometimes you do hyperparameter tuning, obviously. And then the other part is the high sample complexity. Typically, you need a lot of samples to calculate this gradient estimate well, because originally you needed one infinite length sample. You don't have that. So you have to have something good enough that still gives you small residual error in like gradient estimation. And that's why you try to use the previous samples collected from previous policies. You try to do importance sampling, replay buffer. We'll again hear about all of them in later talks. And the final thing is like the stochastic gradient estimators suffer from high variance. Again, people use baseline functions. You can read chapter 10 of Son's book, and then also you can go for actor critic methods, where we don't know how it really like works theoretically, but we know it works. So the next thing is like people go for actor critic methods, and from where the name of the talk is coming, the actors and the critics, because what we have studied in two parts are these value-based RL methods, which are called critics, and the policy-based RL methods, which are called actors. In one case, you learn the optimal value or Q-value function. You design all these algorithms. In another case, you learn the optimal parameterized policy, and you design all these algorithms that you have seen. The pros of the value-based method: it has low variance, good convergence guarantee, but often it scales pretty badly with the very high dimensional data that we want to go for. And then this side, it scales for large state action spaces, continuous states, continuous actions. But the con is high variance and sample complexity. So the whole idea that people came up with next, why not use them two together? So basically, at every point of time, we are still in generalized policy iteration. You get the feedback. You try to evaluate your policy using a critic. Basically, you try to calculate its value function. Then you use an actor, which is a gradient, that tries to improve on the policy you had. Then you take the action, you take the feedback, you try to evaluate your policy again, then improve on the policy using a policy gradient, you take the action, and you go on. Okay, so this is the idea of actor critic methods, where you can put pros of two sides together. It works, but like again, Sean will talk about what are the nuances of like the theory of actor critic methods. This is somewhere again, like if you are searching for problems or if you have no problem, then this is a big one that you should look into. So this slide is for the online purpose. So I'll conclude my talk in here. So yeah, let me know if you have any question or comment. Okay. So, any question? Yeah, sure.
What is the difference between sleeping and separating?
Which one?
In PPO,
Yes.
so it's the main difference between saturating. So we have one plus beta and one minus beta.
Oh, so you clip. So when I mean clip function, it has a max and mean, right?
Yeah.
So the max is 1 plus delta and mean is 1 minus delta.
What is the main difference between it and clipping it in terms of learning?
Oh, in terms of learning, like, so this is a function, this is kind of a constraint optimization problem, right? So you don't want to solve the constraint optimization problem in here. You rather want to say like, I know that this thing can be written as a log ratio of this, right? Which you want to be less than some epsilon. If the ratio itself stays small, the log ratio stays small. And that's the whole intuition. Like, so basically I try to bound the ratio so that everything after is staying bounded, right? So that's why if you see this first term remains the same. But this second term is basically just in a hard way, you are trying to bound the ratio so that the KL will be bounded. So roughly the KL will be bounded by a log of delta, right? Because the KL is expectation of log of this ratio. So think of that.
If we don't go for the tuning, can go unstable faster or in general.
Yes, exactly. So that's why like hyperparameter tuning is a big part of deep RL, right? So that's why you can never ignore it. Yeah.
Then why you're not separating? It will be less risky.
I agree. Like I like to do stat and math. So like I'll always go for the KL thing. But yeah, this is what people like to use in practice because it is cheap, right? Just clipping something is better than solving a constraint optimization problem in terms of speed, right? That's all. Means there's no other magic in here, basically. Yeah. Yes. 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 Yeah, because I think this was, yeah, PPO, they have a KL version of that. Yes, 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 yes. Yes. That one I am always a bit, yeah, yeah. That's always a bit shaky claim. Yeah, but this is faster and like again, you can tune it easily. Like not easily, but like, yeah, tune it. Okay, any other question? Okay, so if not, then thank you. And yeah, let's go for the tutorials in a bit. Yeah. Ah, that slide you want to see? Okay. So what we didn't cover, theoretical guarantees, how to derive them, like the convergence, regret bound, stability analysis, sample complexity bound. So the convergence and stability is one we'll talk about. I'll try to talk a bit about optimism, and I think Mariam and Franz in their lectures also will talk a bit about different types of guarantees. And this other part, like the generalization ability, how you can find out the generalization. So you might not be interested just in the optimal function. You might be interested in the generalizability of the Q function or the policy you have seen. That part is a very interesting but separate style of work. We have not talked about that. The exploration, exploitation, obviously, we have not talked about. And the other question is like, can you be robust and safe while learning and execution? That is the robust MDP and safe RL that I think Mariam will talk about later. Yeah. So, yeah, that's all. At least that's the known unknowns. Yeah. Yeah. Okay.